We're still talking about our normal distribution. This is a feature it has called the empirical rule, or some books call it the 68, 95, 99.7 rule. So in a normal distribution with a mean mu and a standard deviation sigma, approximately 68% of our observations will fall within one standard deviation of our mean. So I'll show you on the graph. Okay, so here's our mean here in the middle. And if you go out one standard deviation in either way, this area from here to here will be 68% of all of your total area. And if you go out two standard deviations in either direction, that will be 95% of your total area. And if you go out three standard deviations, that will be 99.7% of your area. This is really cool because this works for anything that's normally distributed. We can say, oh, if we know it's a normal distribution, we know how much of our data will be within one standard deviation or how much will be within two standard deviations. So let's see, in this example, the distribution of heights of young women is approximately normal with a mean of 64.5 inches and a standard deviation of 2.5 inches. And we want to know what the empirical rule says about this distribution. Well, we know that it's always going to start at 64.5. And then if we go out one standard deviation to either side, so if we go out 2.5, let's go ahead and subtract that. So if we do 64.5 minus 2.5, we get 62. And if we add 2.5, we should get, what, 67? And so our empirical rule tells us from here to here should be 68% of our data. Okay, so it tells us that 68% of young women, let's see, young women's heights will be between 62 and 67 inches. So let's see what happens if we go out two standard deviations. So if I do 62 minus 2.5, I'll get to 59.5. And if I come up here, I'll get to 59.5. So from here to here should be 95%. So inside here was 68%. From here to here is 95%. So that means 95% of the heights should be within or between 59.5 and, oh, I wrote 59.5 again, sorry. That should be 69.5. So 59.5 and 69.5 inches. So this first one was our mean plus or minus 1 standard deviation, or it was 64.5 plus or minus 2 times our standard deviation of 2.5 gave us that range. This one is our mean plus or minus 2 standard deviations, so that's 64.5 plus or minus, oh, sorry. This was supposed to be 1 standard deviation. Here we had 2 standard deviations, so 2 times 2.5. And then our last one should be our mean plus or minus 3 standard deviations. So 64.5 plus or minus 3 times 2.5. Let's see what that would give us. If we do 64.5 minus 3 times 2.5, we get to 57. And this value would be, if we add 3 standard deviations, we get 72. So from here all the way over, this will be 99.7% of our data. So we could say that 99.7% of the heights will be between 57 and 72 inches. So that's what the empirical rule tells us. It lets us kind of figure out how much of our data should be within certain ranges. Okay, there's a chance for you to try. Now we're going to talk about something called standardizing or standardization. So if you have a random variable x that's normally distributed with any mean mu and any standard deviation sigma, you can standardize it with this formula, z equals x minus mu over sigma. The new random variable z has a standard normal distribution with a mean 0 and a standard deviation of 1. Okay. So the z-score is going to tell us how many standard deviations our x value is from the mean. Okay. So notice up here, we were saying, oh, like 62 is one standard deviation less than 64.5, or 67 was one standard deviation higher than our average of 64.5. So here's our graph for that distribution we were just barely working with. So notice we were centered at 64.5, and then each of these tick marks represents one standard deviation. Let's try and standardize a height of 62 inches. So my formula is z equals x minus mu over sigma. So our x value we're interested in is the 62. So 62 minus, let's see, it was a normal. We had a mean of 64.5 and a standard deviation of 2.5. Okay, so 62 minus our mean of 64.5 over our standard deviation of 2.5, which gives me -1. You'll notice I drew these two graphs, and the 62 lines up with -1. The average lines up with 0. 67, which was one standard deviation above, lines up with 1. So that's how you standardize. 62 was one standard deviation below the mean, so z equals -1. So 62 is one standard deviation below the mean, so z equals -1. If I tried another value, let's try it for x equals 72. Then z is going to be our x minus our mean over our standard deviation. So x is 72 minus our mean, which is still 64.5, over our standard deviation of 2.5, which gives me 3. Okay. So that means 72 is 3 standard deviations above the mean. So z equals 3. Which matches our picture because the 72 matched up with z equals 3. So it's basically just another way to rescale our data so it fits that standard normal curve. It's also important because, again, if z equals 3, you know that means there's 3 standard deviations above the mean. So in our next example, U.S. men's heights are normally distributed with a mean of 69.1 and a standard deviation of 2.9 inches. Women's heights are also normally distributed with a mean of 64.5 and a standard deviation of 2.5. So let's write that down. So men, we have a mean of 69.1 and standard deviation equals 2.9. For women, we have our mean equals 64.5 and our standard deviation equals 2.5. Now it tells us John is 74 inches and Chelsea is 69 inches tall. We want to know who is taller for their gender. So obviously John is taller than Chelsea is, but that's because men and women are supposed to be different heights. Which one is actually taller compared to their average? So let's do this by saying who is farther from the average of their gender. The easiest way to figure out who's farther from the average is to find their z-scores. So we'll find each z-score. So again, z equals x minus mu over sigma. So let's find the z-score for each one of them. So for John, his z-score, he is 74 inches. So 74 minus, make sure you do the mean for the men, 69.1, and standard deviation for men. 1.689. And let's do Chelsea. Her z-score is, we're going to do the x for Chelsea minus the mean. Make sure you do the mean for the women. Divide by the standard deviation for the women. So her x value is 69. Her mean is 64.5. And her standard deviation is 2.5. So her z value is 1.8. So let's write out here then that John is 1.689 standard deviations above the men average. Chelsea is 1.8 standard deviations above the women average. So Chelsea is taller for her gender. Okay, so she had the higher z-score, so she is actually the one that is taller when you compare them to just people in their gender. There's one for you to try. Let's see, this one we're actually going to work backwards. So Harrison is told he is 1.3 standard deviations above the average height. How tall is he? So in this one, he has a z-score of 1.3 because he's above the average by 1.3 standard deviations. That means he has a z-score of 1.3. And we want to find his height. Okay. Well, we know our formula is z equals x minus mu over sigma. And in this case, we would know everything except for the actual x value. So let's plug in what we do know. So his z value is 1.3. We don't know his actual height, which is the x. The mean, he's a man, so the mean is 69.1. The standard deviation is 2.9. So we have all of this, and we're just going to solve for x. So multiply both sides, so we'll have 1.3 times 2.9, and then we'll add 69.1, and that will give us our x. So x is going to be 72.87. So if he's 1.3 standard deviations above the average, that means that his height is 72.87. There's another problem for you to try, and then we have this problem. Okay, so you'll notice this one I termed a problem instead because we haven't actually figured out how to do it yet. So in this one, we found Chelsea's height of 69 inches, had a z-score of, let's go back up and look at Chelsea. Chelsea had a z-score of 1.8. So here's my z-score of 1.8. And let's say we want to find the percentage of women that are shorter than Chelsea. Well, we haven't done anything like this yet, but we did actually learn how to find probabilities for z-values for our standard normal distribution. So we're really looking for the probability that z is less than 1.8. So remember how we did this before? We did a normal CDF. We did a mean of 0 and a standard deviation of 1. And we want to see the ones that are less than 1.8. So that will be from 1.8 to like negative 1 million or something like that to put it into my calculator. So let's pull up my calculator again. So let's do our distribution menu to get to a normal CDF. My lower bound is this negative 1 billion or million or something. My upper bound is 1.8. I still have a mean of 0 and a standard deviation of 1 because the z-score, z is always for the standard normal distribution. Remember, you did all of those problems with the standard normal distribution, and that always has a mean of 0, standard deviation of 1. So we get 0.964. So this probability, or the probability of z being less than 1.8 is 0.964. So this means that 96.4% of people are shorter than Chelsea, or women, not people. Okay. So for this problem, we had to do it in 2 steps. So we had to find the z-score, then find the probability. Now it turns out this is what we used to do all the time. Okay, so we used to standardize, find the z-score, and then use a standard normal table. But now we can actually put it all straight into our calculator. Okay, the reason why is calculators let us do it for any mean and any standard deviation, so I can skip the whole standardization part. It's still useful to know how many standard deviations something is from the mean, so we'll still kind of keep that around. But as far as using it to find probabilities, we'll just go straight into our calculator now.